Okay, any new questions during the break? Somebody has forgotten his or her pen. Any questions? I had received some nice questions during the break, which started with the phrase, I have a stupid question. Any other questions which we would like to start with a stupid question?
You asked the R squares. Is it because they are both like fields forces?
What does it mean to be like fields forces?
I don't know, like there's a gravitational field, there's an electric field.
We will define those. I mean, ask me this question when we discuss Gauss's law. Now, before we come to start discussing the concept of fields, let's do a couple of simple examples. Now, even before the examples, you see here, some of you were asking why did I draw them to be pointing in opposite directions? Or won't they be towards each other if the forces are the opposite forces? Or the charges are unlike charges. Well, yes, they will be. If they are unlike charges, they will be towards each other. In this sketch, at least, I had to choose some direction. So I just chose it such that these force directions are correct if the two charges are the same direction. Now, when you are solving a question or when you are making an analysis, just starting by saying, if the charges are same, I will use this direction. If the charges are different, I will use the other direction is not so useful. It just becomes so messy. Rather than that, what we do is we just write the law in the form of, okay, the magnitude is this one. Let me use this notation. This is the force acting on charge 1 due to charge 2. Okay, let me write it also over here. This is the force acting on Q1 due to Q2. And this R12 is a unit vector. This is R. Is a unit vector pointing from charge 2 to charge Q1. So basically, well, if you would just sketch a couple of cases, let's say this is Q1 or this is Q2. This is Q1. If we have such a system, R12 is the unit vector pointing from Q2 to Q1. So R12 is this vector, or on Q1 it is in this vector. This is my unit vector. So let's see if Q1 and Q2, they are the same charges. They can be both negative, they can be both positive. Then their product is positive. So if, now the force is over there. So this is a positive number. This is a positive number. This is a positive number. So if Q1 and Q2 are the same, then F12 is in the same direction of R12. If they have the same sign, which basically means Q1, Q2 is larger than 0, then F12 is in the same direction. As R12. Now, if they have the opposite sign, then Q1, Q2 is less than 0, which basically means that F12 is in the opposite direction. As R12. So why is it that? Well, you see, this is the expression of our force. If Q1 times Q2 is a negative, multiplying a vector by a negative number just means that multiply the magnitude of the vector by the magnitude of the negative number and reverse the direction. So if Q1, Q2 is negative, then Q1 times Q2 times this vector already points in the opposite direction. And that opposite direction, if we have if these are two different, if they have different signs, the opposite direction to R12 is pointing from Q1 towards Q2. So if you write the force in this form, in vectorial form, you don't need to worry whether the charges have the same sign or not. It's automatically already included in this expression. Of course, if you try to sketch the direction of the force, you will need to pick up a direction. But besides that, in your computations, you don't need to worry about whether it's pointing in one direction or the other one. Now, this is for, as I said, this was for point systems. What happens if we don't have point systems? Well, just like you did in your mechanics courses, for example, you already also studied extended objects. What you do when you were studying the gravitational force exerted by extended objects on each other was you just divide it into very small parts, and each very small part just behaved like a point object and sum the vectors. Well, basically the same phenomena appears over here. The electric force it satisfies the superposition principle. Well, what does it mean to satisfy the superposition principle is, let's assume that we have a charge over here, another charge over here, and this time a third charge over here. And we would like to know what is the electric force acting on this charge Q3. The force acting on the charge 3 will be just the force acting on the charge 3 due to the charge 1, plus the force acting on charge 3 due to the charge 2. This is the force we have. So just calculate the force this one has. This one has, sum them vectorially, not just the magnitudes. You have to take into account their direction. Now, just for the purpose of the sketch, let me just assume that all of them have the same sign. So this Q1 will exert a force on Q3, and it will be pointing in this direction. This is what I call F31. And similarly, Q2 will exert a force on Q3. It will be pointing in this direction. Let's call that F32. Do you remember how you add the vectors? Well, that is one way, but just for the purpose of the sketch, you can just do a parallelogram. So this is where they intersect. So this is my F3. This is the net force acting on the charge Q3. So if you know its mass, you can also calculate its acceleration and see how it will move. So let's do a concrete example. This is problem 20 in your book. So there is a wall, and two charges are suspended from the wall. And they the length of the ropes are identical. They are charged. So if I have such a configuration, can you say anything about their charges? Will they be the same or opposite? I can say that they have the same charge, same sign. They are repelling each other so that they open up. So if they are at rest in this shape, I definitely know that Q1 and Q2, they have the same sign. You agree? So that is already one thing that I know. I don't know what their ratio is, which one is larger, which one is smaller, but I definitely know that they have the same sign. And let's call this angle theta 1, this angle theta 2. And we are also given that theta 1 and theta 2 are small. They are much less than 1. Well, basically, that small angle will tell me that tangent of these angles are approximately equal to their sine, which is approximately equal to the angle itself. Okay, so let's see what the question asks. Okay, in part A, it says Q1 is equal to Q, Q2 is equal to 2Q, and M1 is equal to M2 is equal to M. If these are satisfied, what can you say about theta 1 over theta 2? How do you know? Well, I can tell you, yes, how do you know? Yes.
Because the forces are the same.
Okay. Are the forces acting on these two masses the same?
No, not all.
Okay, so all the forces are not the same.
Yes.
So do you still stick with your idea that it should be 1?
Yes, just
Okay.
the electric.
The electric forces are the same.
Yes, and the gravitational force are the same because of the mass.
Okay.
So the forces
All the forces are the same, just pointing in, the electric force pointing in opposite direction. So the ratio should be 1. Do you agree? Anybody who doesn't agree? Okay, yes, that's correct. Well, let's go to the other case. Q1 is equal to 2Q, Q2 is equal to Q. Now, Q1 is equal to Q. Again, the charges are the same. M1 is equal to M, but M2 is equal to 2M. Q1 over, theta 1 over theta 2 in this case. Can they be 1 to start with? Yes or no? Why not? So what does it change? The gravitational force will be different, right? So in the previous case, although the charges were different, they were exerting the same electrostatic force on each other. They had the same mass, so the gravitational force was the same. So the forces were the same, the except that the direction of the electrostatic force, everything is the same for both masses. So that's why we had theta 1 is equal to theta 2. But now, again, we have the same forces. You see, we are changing the charge, but it doesn't matter. It's the product of these two charges which determines the force that two charges exert on each other. So it doesn't make any difference which one has a larger or which one has a smaller charge. So the electrostatic forces they exert on each other are the same, but the gravitational force exerted on M2 on the charge Q2 is twice the gravitational force exerted on charge Q1. So the angle will not be the same. So if I would sketch it over here, this is my Q2. There is a electrostatic force, let me call it F2, and then I have the gravitational force, 2mg. On the other one, this is F2, and then this is just mg. So how can I relate the angles to the forces? Eventually, I need to evaluate the angles. How can I relate the angles to the forces or some other property of my system? Okay, so what about? These are already components if I choose the x and y axis like that. So the y component is 2mg, the x component is f2. How do I relate that to theta 2? Tangent. So basically the resultant force, you see, there's a tension over here pulling it in that direction. It is at rest, it's not accelerating. So Newton's law tells me that there should be another force in the opposite direction. Well, the only forces I have are these, only other forces I have is these two. So their sum should be in the opposite direction. Along this line, it should be along this line and exactly in the opposite direction. So since this is parallel to this one, the angle over here is theta 2. So tangent of theta 2 is f2 over 2mg. No, this is f1, sorry. Similarly on the other side, so if I just extend this line of the string, the resultant force should be exactly in this direction, and that is theta 1. Tangent theta 1 is f1 over mg. Now, in the question, we are already given that theta 1 and theta 2, they are very small angles. So what that means is tangent of theta 2 is approximately theta 2, and tangent of theta 1 is approximately theta 1 in units of radians, not in degrees, in units of radians. So if you want to calculate theta 1 over theta 2, well, theta 1 is f1 over mg. 1 over theta 2 is twice mg over f2. Mg is cancelled. What is the ratio of f1 to f2? 1, because the two charges exert exactly the same force on each other. They cancel, so we end up having 2. Well, there's one more approximation we did in the calculation. Can you point the approximation we made? Okay, one approximation was this one. There is another thing we assumed, which is not exactly correct. What do you mean by tension? Okay. So, what happened to the tension of the ropes? Okay. Some other ideas? There was somebody over here.
Maybe the sign must be minus because the forces are in the opposite direction.
Well, it depends on your convention. I define this angle to be positive, this angle to be positive. The ratio has to be positive. So the sign is not a problem. There's another approximation I made, though.
We assume electric forces are horizontal, stay horizontal.
Okay. Why shouldn't they be?
Because if the growth length of groups is equal, Q1 will be higher, and it's not become horizontal change angles.
Great, that's the idea. So you see here, if you plot draw the horizontal line, the centers of these two spheres, they are not horizontal because, well, one of them is open more. So it is higher. This one is higher than this one. But already the angles were small. We are given that the angles are small, so this shift in the vertical position, we can just ignore. So, okay, we just use the fact that the angles are small when we assume the vertical components of these vectors, and also we used it over here. Within this approximation, we have the ratio is approximately 2. Any questions? Now, by using the superposition principle, in fact, if you have a charged extended object and another charged extended object, you can just calculate the forces that they will exert on each other. The idea is you just divide each one to very small pieces, so small that we can treat them as point-like, and sum all the forces that each one of these point-like objects exert on each other. And in the limit that these very small pieces go to a 0 dimension, you have infinitely many of them. So you have a sum which has, each term in the sum is very small, but you have infinitely many of them, and that is what we call the integral. So eventually you can write it as an integral. But most of the time, rather than calculating the force on the between extended objects, what we do is we just divide it into two parts. First, we calculate what is called the electric field. Well, there are a couple of motivations for defining the electric field. If you look at the Coulomb's law, so let's say if there's a charge over here, another charge over here, this charge directly exerts a force on the other charge. This is what we call action at a distance, just like in gravity, in Newton's gravity. Action at a distance is quite problematic. It's not even a consistent definition. Especially with the discovery of special theory of relativity, we now know that this shouldn't work. Action at a distance shouldn't exist. The charge, if you have these two charges, Q1, Q2, the force that the charge, let's say Q2, feels should be due to something at the position of the charge Q2, not due to Q1. Of course, Q1 might be creating that, whatever it is, which then exerts a force on Q2. Now, that thing created by the charge Q1 at the point Q2 is what we call the electric field. And we define the electric field as, well, you just take a test charge. Let's say instead of Q2, here you put a charge Q. That is our test charge. There is a force that test charge feels, and you divide it by Q, and take the limit as Q goes to 0. This is how we define it at a given point. This is the electric field at this point, let's say P. So the electric field at the point P is defined like this. You just take that, go to that point, put a very small test charge, and calculate the force that test charge feels, divide by the magnitude of the charge, and you get take the limit that this charge goes to 0. Well, to be precise, you can never take the limit of the charge going to 0, because limit is defined only for continuous objects. Like in the calculus course, you are probably seeing the limit of functions as a function of x as x changes continuously and approaches some given value. But we know that charge does not change continuously. You can either add one electron or remove one electron from a system. You cannot just change it whichever way you like. But still, the charge of the electron is so small that we can just somewhat ignore that discreteness for most practical purposes. So this is what it should be understood in this limit, by this limit. So it's so small that the discreteness of charge, the charge of an object can only be multiples of the electron charge, positive or negative multiples. But that discreteness is so small, we kind of ignore it and write this definition. So how does this solve our problem of action at a distance? Well, what happens is at this point, if you have a charge Q1, it creates an electric field everywhere. So if I put a charge over here, it feels the force divided by the charge of that charge, and that gives me the electric field. A non-zero electric field there, a non-zero electric field there. In fact, this point charge fills the universe with an electric field. And if I bring another charge over here to Q2, that charge Q2 will feel a force. You see, just kind of inverting this, the force that the charge Q2 will feel is just the electric field at the position of the charge Q2 multiplied by the charge of Q2. So you see, the force that a charge feels is created by the electric field at the position of the charge. So there's no action at a distance anymore, at least in this expression. Now you should be complaining. Any questions? Well, we didn't actually solve anything by just writing in this form. We just kind of hid it in this expression. But at least within this framework that we have discussed up to this point, well, the electric field is created by something very far away. So still we have action at a distance. So up to this, at this point at least, this is just kind of a mathematical definition without any other physical intuition, let's say. But eventually, towards the end of the semester, we will see that this electric field actually has its own physical existence, its own physical properties. Well, even probably within a couple of weeks, we will see that if there is an electric field, there is energy there. The property that we assign to physical quantities, it has energy. We will see that it has, well, not just the electric field, with the magnetic field, it has momentum, it has its own existence. But for the time being, it's just a mathematical tool. Well, how do we calculate the electric field? Let's go a couple of examples. Let's start with the simplest example of a point charge. Well, we put the charge over here. Let's say I would like to find the electric field at this point, P. And just for simplicity, let me show this vector pointing from the charge Q to the point P as the vector R. It can be any point P. Well, to calculate the electric field, we will just use the definition. I will put a test charge over there. What will be the force that the test charge will feel? Okay, somebody? What is the... I put a charge Q. I have a capital charge Q over here. What will be the force that that test charge will feel? Okay, kq, I heard somewhere, times small q divided by r squared in which direction? I'm looking at this, you see, I'm looking at the electric field at the point P. So to calculate the electric field at the point P, I have to calculate the force acting on the test charge that I placed at that point. So that's the point I'm looking at. So what will be the force acting on it? Its direction? How can I write it over here? Well, this was the vectorial notation we use. If we don't want to deal with possible various cases, like if this charge is positive, this one is negative in this direction, in the other case in the other direction, well, we can use this concise vectorial form. Again, if we just repeat, well, this is the magnitude, let's say, of the force, and this vector is pointing, this is the force felt by the charge at Q1 due to the charge Q2, and this was the vector pointing from the charge who is creating the force towards the charge that is fielding the force, this vector. Now in this example, the charge creating the force is Q. The charge fielding the force is small q. And the vector connecting large q to small q is just this vector. So I have to write the unit vector in that direction. So whatever the signs of these charges, this expression will always hold. Whether whether they are opposite charges or same charges, this expression will be always correct. Do you remember vectors? Do all of you remember vectors? Shall we make a short review? Okay, so let's just take a 5-minute review of vectors. What we mean by a vector is a number, which we call the magnitude, and direction. So if we want to write down quantities that should have a direction, like forces, it's unavoidable that we use vectors. So what we say is, let's say, the force is 5 newtons in that direction. That's a vector, because I talk about the magnitude and the direction. Now, the easiest way to work with vectors will be in terms of its components. If you just choose some axis in some direction, again, it's completely arbitrary which directions you choose. If you have a vector, this is v, well, you just draw the vertical line to the x-axis and the horizontal line to the y-axis. So this length, this point is vx, and this point is vy. So, or this length is vx, the magnitude of vx, let's say, and this is the absolute value of vy, because vx and vy, they can be negative. If they are on the other sides, they will be negative. So at this angle over here, let's say theta, tangent theta is just vy over vx, or if you know the angle theta, then vx is v times cosine theta, and vy is v times sine theta. Because here, you see there's a right triangle. There's a right triangle with the angle theta. So I'm just using the definitions of sine and cosine. Well, these expressions are valid whether theta, in this figure I just plotted theta to be between 0 and pi over 2, 0 or 90 degrees, but whatever the value of theta is, this will always be true. As long as theta is the angle, I define it to be positive in this direction, theta is the angle between the vector and the x-axis. if my vector is something like that, my theta angle will be all of this angle. It will be larger than 180. So with those conventions, these are still whole. What else we are interested in is, like in the superposition principle, we are adding forces. Forces are vectors, so we should be able to add vectors. So if I have a vector v, I have the components, you see, I have the component Vx in the x direction, plus I have the component Vy in the y direction. Or, I think in your book it was Vx in the I hat direction plus Vy in the j hat direction. It's just basically the same thing. If you have a second vector, let's say this is, if you have V1 with components V1x, V1y, and let's say V1z, k hat. And now you have the second vector, V2x, V2y, V2z. Well, the sum if this is, let's say, V1, this is V2, well, geometrically, you just take V2 and copy it to the tip of V1. I have this V2, just copy it to V1. And then the sum vector is just this vector, let's say V. V is V1 plus V2. In terms of the components, what you do is, if you just sum the vectors, you just add the corresponding components. This is V1x plus V2x plus V1y plus V2y plus V1z plus V2z. And if you want to multiply V1, let's say one of the vectors, by a number, well, geometrically, this is a, okay, you see, a vector is a magnitude and a direction. So if you know the magnitude and the direction of a vector, you know the vector. Now, this vector is defined as a vector whose magnitude is equal to a times the magnitude of V1, and whose direction is the same as V1 if A is positive and opposite of V1 if A is negative. So let's say you say that, okay, your house, let's say, is 5 times in that direction, 5 times 1 meter in that direction. So what you do is, if you want to, this is a vector, in that direction, 1 meter. If you want to multiply it by 5, what you do is, it's a positive number, it's still in that direction, but instead of 1 meter, you just go 5 meters. If you multiply this vector by -5 rather than 5, again, you go 5 meters, but exactly in the opposite direction because the coefficient is minus. And in terms of components, this a times V1 vector is a times V1x in the I direction plus a times V1y in the j direction plus a times V1z in the k direction. It's just like when we are summing in terms of components, we are actually summing the components. When we are multiplying a vector by a number, we are just multiplying the components by that number. And in fact, this is all you need to know about the vectors. We don't need to know anything else. So just keep in mind that They are just whenever we are talking about a vector, we are talking about a quantity which has a size and a direction. And when we are doing manipulations in terms of vectors, when we are adding vectors, you just either think of adding them, just drawing them one after the other. This is how you add them, or you just add the components. When you are multiplying them, well, multiplication is kind of addition. But you are adding the same thing over and over again. So you are basically going either in the same direction, or if it's a negative number, you are going in the opposite direction. But it's again a vector pointing either in the same or the opposite direction of v1, whose magnitude is the magnitude of a times its own magnitude. Now, we will use these. Now, any questions do you have about vectors? When we study magnetism, we will be also talking about the products of vectors, the vectorial products, but I will leave that discussion to magnetic fields. Okay, let's go back to electric fields. Okay, one example we had already seen, we had discovered now we didn't yet discover. So does this notation make sense now? It is more sense, let me say. The hat basically means that it's a unit vector in the direction of the r vector. Here I define my r vector. A unit vector is a vector whose magnitude is 1. So this is a vector with unit magnitude in that direction. So I know the magnitude, I know its direction. So I know that vector. And I'm just multiplying that vector with a number. So if I know the components, in a concrete example, let's say, if I know the components of this vector, I can calculate this unit vector, I can calculate this number, and then I know what the force is. And, well, let's continue. The electric field was defined as the force divided by Q. Well, the force we had already written, K Q times small q over r squared. This is the force in this direction, times 1 over q. So they cancel. Once I cancel these test charge, the charge of the test charge, well, nothing depends on the test charge anymore. So I can just, the limit is just whatever remains. K times q over r squared in the r direction. So if here I have my charge, if I want to find the electric field, let's say at this point over here, at this is my charge Q. The electric field at this point is, well, I have to measure this length. That will be my R. I know the charge of my particle. This is just a constant, a known constant. And this r vector, the unit vector, is pointing from the, if q is positive, it is pointing from the charge to my point P. If it is, well, it will be in that direction at this point. If q is negative, it will be just in the opposite direction. So just for the purpose of the sketch, I will assume that q is positive. So at this point, the electric field will have this magnitude, this direction, and somewhat this magnitude. If I go further away, let's say at this point, the electric field will be in this direction. It will be smaller. If I go even further away, it will be again along this line joining my point P to the charge Q, and it will be even smaller and pointing in that direction. So wherever I go, this electric field is always in the direction connecting my charge to my point. It's in that direction, etc. So at every point in space, there is an electric field vector. That's why, in fact, it's called a field. Mathematical definition of a field is at every point it assigns some quantity. Like the electric field is what we call a vector field, because at every point there is a vector. And here it will be in this direction even smaller. Any questions? Well, rather than, what we usually do is, rather than just imagining a vector at every point, because if you want to plot a significant number of points, well, you would like to put some vector over here. If you want to try to draw the vector field over here, it will overlap with this one, so it won't be. It will become a mess. So rather than just drawing these vectors at every point, what we do is we draw vector lines or field lines. Well, essentially, what field lines do is that, let's see, at this point, I'm very close to the charge cube. At this point, the electric field will be pointing in that direction. And it will be huge. At this point, it will be still in the same direction. It will be a bit smaller. At this point, still in the same direction, somewhat even smaller, etc. So when I am drawing electric field lines, I start from the positive charge, start to draw lines such that at every point, you see, at every point we have a vector. And if you imagine a line, at every point the line has a tangent line. So we draw these field lines such that at every point this field line, the tangent of this field line, is in the same direction of the electric field. So for a positively charged, the electric field is always pointing away from the charge. That basically tells me that the field line should be always moving away from my charge. So this is the electric field line. This is another electric field line, etc. You can just draw as many electric field lines as you like. They are always tangent to the electric field. So if you take this point, the electric field line at this point is tangent to this line. If you take this point, the electric field at this point is tangent to the field line passing through that point. So that allows you to determine given the electric field lines, this allows you to determine the direction of the electric field. And the magnitude of the electric field is proportional to the density of electric field lines. You see, at this point, you first fix the number of electric field lines you have. Once you fix it, you see, at this point, the density is much higher than the density of electric field lines over here. That basically means that the electric field at this point, the direction you already know from the field line, the tangent to the electric field line, and the magnitude is proportional to the density. If the density of field lines over here are twice as much as the density from here, then the electric field line magnitude at this point is twice as much as the magnitude of the electric field line at this point. Anyway, they will be kicking us out. So if you have any questions, we can continue outside. So see you on Monday.